All right, ladies and gentlemen, so today we are going to introduce polynomials and our big unit on quadratics. So make sure that you go into Teams and find the table of contents, or wait till you're in person this week so you can glue that table of contents into your notebook. For this unit, the two skills we're going to start working on are we're going to be interpreting parts of the expression, such as terms, factors, and coefficients, and we're also going to understand that polynomials form a system analogous to integers. So what we're doing is we're going to talk about polynomials, but we know that they follow the same rules as integers or numbers when we're dealing with expressions and equations. To do that, we have some vocab terms. The first vocab term today is the idea of a polynomial. A polynomial is the addition or subtraction of variable terms with non-negative integer exponents. Non-negative meaning positive, and integer meaning counting numbers. So we're not going to be dealing with things raised to the power of 2/3 or anything like that that we've dealt with our exponent rules. These are just going to be our positive integer exponents. But to do that, we can describe them in different ways. We can describe our polynomial by the number of terms that we have. If we have one term, we have a monomial. If we have two terms, we have a binomial. If we have three terms, we have a trinomial. And we could go on, but these are the three ones that I want you to know that you can use to describe your polynomials. The other piece that we can use to describe our polynomials is we can describe the degree. The degree tells us the greatest power or exponent of any term in our polynomial. And so this little chart here can help you out. If I have a constant, just a number like the number 2, well, that's really a polynomial with a degree of 0, because 2 is the same thing as saying 2 times x to the 0th power. I know from my exponent rules that anything raised to the power of 0 is 1. So 2x to the 0th power is the same thing as 2 times 1, which is 2. Well, I can have a degree of 1, and I would have a linear equation. The best example of this would be like in slope-intercept form. I could have y equals 7x plus 4. That 7x plus 4 is a linear or a first-degree polynomial. Second-degree polynomials are going to be our quadratics, and we're going to spend a lot of time on it in the next 2 units here. That's when I have x squared as my highest power. And I can go on. I can have third, fourth, fifth, sixth, or higher degree polynomials. But what we're going to focus on in this unit is mostly this 0 to 2 second degree polynomials. Last vocab term for this section is a leading coefficient. A leading coefficient is the coefficient of the first term when written in standard form. So that idea of standard form is where I order my terms in my polynomial from the highest power to the lowest, and the leading coefficient is whatever number is attached to, let's see if I have x to the 7th, whatever number is attached in front of that highest power. So let's practice with this. What I have here is I have a polynomial, or I have to write it in standard form, identify the degree, the leading coefficient, and the type of polynomial. So this one here is a polynomial. Standard form means that I need to order it so that I have the highest power first. When I see this here, the first thing I want to do is I need to remember where those negative signs are attached. So 3x squared minus 4x to the 5th plus x is really the same thing as 3x squared, oops, let's erase that and try again, plus a negative 4x. That negative is really attached to that 4x. I think it's easier if we think about addition and then change it to negative terms instead of having subtraction looped in there. Well, standard form tells me that I need to take that highest power first, so I have a negative 4x to the power of 5. And then I find my next highest power. That's a positive 3x squared. And then my last piece is plus x. The degree on my polynomial is going to be that highest power. So my degree in this case is 5. It's the 5th degree. My leading coefficient is going to be negative 4. Leading coefficient. It's going to be negative 4. The leading coefficient is the number attached to my highest power. The type of polynomial, well, that just asks me to count the number of terms. So in this case here, I have a trinomial. I have 3 terms. So standard form, I've ordered it from greatest exponent to smallest exponent. It is a 5th degree polynomial because my highest power is a 5. My leading coefficient is negative 4 because that's the coefficient attached to the highest power exponent. And it's a trinomial because I have 3 terms. Well, now with these ones here, I want to identify if they are polynomials or not. If they are a polynomial, I want to identify the degree and leading coefficient. But if it's not a polynomial, I need to explain. So if my first example on this slide here is 5x plus 4. Is it a polynomial? Well, yes. Yes, it is. It is a linear polynomial with a degree of 1. I see that exponent with a power of 1, so the degree is 1. My leading coefficient is the coefficient attached to my highest power exponent, so my leading coefficient is going to be 5. This next term here, I see 9 over m. Well, if I rewrite that so I have it without that fraction bar, I know that this is equivalent to 9m to the negative 1. If I'm thinking about those exponent rules, if I want to take it from the denominator and put it in the numerator, my exponent becomes negative. Now in this case here, this one is not a polynomial. Not a polynomial. Well, why is it not a polynomial? If I look at this exponent here, I know that I need to have positive integer values for my exponent, and this one has a negative exponent. So this one is not a polynomial because of that negative exponent. The next one, I see 3 times 1/2 to the power of x. This is that idea of exponential decay that we explored in chapter 7. And this one, again, is not a polynomial. By definition, a polynomial needs to have that integer non-negative, there we go, trying to talk and write at the same time. It needs to have a non-negative integer exponent, and in this case our exponent is x, so the exponent breaks the definition of our polynomial. For the next one, I see x to the 4th plus 3x squared minus 7. This one is a polynomial, yes. It fits the definition. The degree, well, the degree asks about the highest power. In this case, the degree is 4. And my leading coefficient, if I look at x to the 4th, the invisible number hanging out in front of that x is a 1. Not a 0, a 1. My leading coefficient would be 1. Now this last one is tricky. Technically, yes, this is a polynomial. If I wanted to write it with a variable in it, I could say that it's 7 times x to the 0th power. So it is a polynomial, and in this case, the degree is 0. It's a constant. My leading coefficient, again, I can describe it as that number attached to my highest power exponent. So in this case, my leading coefficient is 7. So we can identify our polynomials, and then we can figure out the ones that aren't polynomials, what part of the definition they break. And in both of these cases here, it's that idea of a non-negative integer exponent. But now we want to think about how we can start combining our polynomials, how I can add or subtract them. If I take a look at all these numbers here on the page, there are some pieces that I can put together, and there are some pieces that I can't. So if I look at this here, I see all my constants. So let's just pretend I dropped all these tiles on the ground, and I want to add them together. Well, I can add 77 and 5 and 16 and 99 and 100. Those are all constants, so I can add them together. Well, now let's look at our x's. So I have a negative 10x. I can add x to that. I can add 5x. I can add a negative 2x. Well, then the next step is I want to find those x squareds. And so x squared is just like x. I could call it y. I could call it b. I could call it a pizza. I can take one pizza and add 4 more pizzas, and then take away 3 pizzas. Remember, our definition of a like term is any it needs to have the same variable raised to the same power. So if I have x squared, I can put together all my x squareds. Last piece, I can do the same thing with my x cubed. I can put together all of the pieces that have x to the power of 3. But at that point, I'd be done. I'd have whatever I had for my green x cubed. I'd have my, what color were they? Purple. X squareds. I'd have my blue x's, and then I'd have my constants. And that'd be it. I couldn't combine them any farther because at that point I would not have like terms. So this one here just shows you the same thing, different colors, but we can put together our like terms and only our like terms. So to practice with this, let's try adding together these two polynomials. I have two trinomials here. They're already ordered in standard form from my highest exponent to my smallest exponent. And I'm going to show you two different ways to add these together. This one here, I'm going to do using our vertical method. So these are added together, so I know that that means that those parentheses don't really matter because I can use that commutative property of addition where 2 plus 3 is the same as 3 plus 2. So I'm going to rearrange it, or I'm just going to get rid of my parentheses here because I know that this is the same with or without parentheses. So I have a negative 3x squared minus 8x plus 5 plus x squared minus 6x plus 2. Well, I know that minus is really the same thing as plus a negative. So what I'm going to do is I'm going to solve this vertically. So I want to stack my like terms on top of each other. So this x squared, I'm going to stack underneath my negative 3x squared. My minus 6x, I'm going to put underneath its like term. And the plus 2 is going to go underneath its like term. So now I can get rid of that because I have set this up as an addition equation. I can put together those like terms. A negative 3x squared plus x squared gives me a negative 2x squared. Negative 8x plus a negative 6x is plus a negative 14x. And 5 plus 2 is 7. I've put together all my like terms, so at this point I'm done. There's nothing else I can put together. For my final answer, I can take that plus a negative and turn it back into subtraction. So I get negative 2x squared minus 14x plus 7. I can add together my polynomials using this vertical method. Well, this time I want to subtract polynomials. So I have q cubed minus 7q squared minus 3q minus q, the quantity q cubed plus 10q squared minus 4. Well, in this case here, because I have subtraction, I'm subtracting each of these pieces. So that's really the same thing as multiplying each piece by a negative 1. So when I rewrite this here, I need to get rid of the parentheses, and I'm going to rewrite it with the appropriate symbols for positives and negatives. This first one here stays the same. Q cubed minus 7q squared minus 3q plus, I have negative 1q cubed plus a negative 10q squared plus negative 1 times a negative 4 is plus 4. So now I can use the vertical method, or this time let's do it just in our horizontal fashion here. I have q to the third plus a negative 1q to the third. Well, that's going to cancel out. Positive 1 and a negative 1. I have a negative 7q squared and a negative 10q squared. So that gives me a negative 17q squared. Now it's done. I'm left with a negative 3q, and I have no like term, so I'm going to put it back in my final answer. And then a plus 4, my last piece, with no other common or like terms. So my final answer is negative 17q squared minus 3q plus 4. I have a trinomial with 3 terms here. This last practice problem is out of the homework, and it's a 2-step one here. So we'll go through the pieces of it and then make sure that you have it written in when you're grading your homework. All right, so I think the last slide cut off. So let's try this again. We're going to practice with one of our homework problems here. This is number 51 from the assignment tonight. In a rapidly growing school system, the number in hundreds of total students is represented by n, and the number of students in kindergarten through 5th grade is represented by p. These two equations model the number of students enrolled from 2000 to 2009, where t is the number of years since 2000. So the first thing we need to do with this information is we need to write an equation that models the number of students S in grades 6 through 12 enrolled for this time period. So the first thing I'm going to do is I'm going to draw a little picture to help me understand what's going on here. The first thing I'm talking about a school system. So I have kindergarten through 12th grade. And I know that total students is represented by n. So I know that from kindergarten to 12th, I have n students. I have that equation. But then I also have an equation for p. P is telling me kindergarten through 5th grade. So kindergarten through 5th grade. is telling me P. And I want to know the number of students, S, for 6 through 12. So I want to know this last piece here from 6 through 12 for S. So I need to figure out how I can take N and P to find S. Well, if I use my little diagram here, I see if I have N and I take away P, I am left with S. So I think this diagram can help explain that big idea here. So my equation for S is going to be N minus P equals S. Well, that's not quite enough for part A, because now what I want to do is I want to take my equation for N and my equation for P and write a simplified version to find the equation for S. So N, let's use the same colors here. I had red for N. So the equation N is represented 1.25 t squared, there we go, minus t plus 7.5. And from that, I'm going to take away P. So I'm going to write it in that vertical stacking. I'm going to have minus my equation for P, which is 0.7 t squared minus 0.95 t plus 3.8. And this is going to give me S. It's going to give me that yellow S that I had here. Well, now, because I'm subtracting, I need to make sure that I keep track of that negative. So for my like terms here, I see 1.25 t squared, and then I have minus 0.7 t squared. So that's going to give me 0.55 t squared. Well, then I have a negative t minus a negative 0.95 t, which is the same thing as a negative t plus 0.95 t. So that leaves me with a negative 0.05 t. And then I have 7.5 minus 3.8, which gives me 3.5. And at this point, I'm done. This equation, this is what S equals this stuff here, because there's no more like terms that I can put together. So now the equation that models S is represented by this yellow box here. The last thing I want to do with that is I want to figure out now how many students were enrolled in grades 6 through 12 in the school system in 2007. So what I'm going to do for that is I'm going to take this equation. So this equation S tells me the number of students in grades 6 through 12, and I want to know in 2007. So my original equation, T was the number of years since 2000. So in this case, I want T to equal 7. When I do that and I go through each step here, we can solve it out. I have 0.55 times 49 minus 0.05 times 7 plus 3.5, and I find out that I get 30.3. But that's not quite my final answer yet, because now I need to figure out what is that number telling me. Well, I know from my original information here that the answer I get is the number in hundreds of total students. So I have 30.300 students in grades 6 through 12. I could write this out as 30.300 students and put a box around it, but because I'm talking about hundreds, I think it's most useful to turn that into a number of students. What I do then is I'm going to multiply that by 100, and I find out that that's equivalent to 3,030 students. 3,030 students. My face kind of got in the way there. So my final answer for B would be that 3,030 students. It would be correct to do 30.300 students, but again, it makes more sense to turn it into one final answer here. Alrighty, so your job now is this homework task here, page 468, number 3 through 42, multiples of 3, and then 51 through 53. We just did 51 together, so if you've got that in your notes, you're ready to go. The other thing I'm going to do in this unit here is I'm going to try to keep track of which Delta Math skills match with each lesson. It's still up to you to do the Delta Math at your own pace. You can save it till right before the test and use that as your review, or you can work on it with each lesson as we go through it. The one thing that I will say is if you are struggling and you're not sure you're doing the homework right, or if you do the homework and find out that you did them incorrectly, I would go into Delta Math and find those skills that we worked on so you can get that instant feedback and figure out what you should be doing to solve these ones. In this case here, the lesson that we just learned matches up with the first 3 skills listed in the Delta Math task for this unit. Go ahead, get to work. Make sure you leave space for that table of contents if you're working on this at home today. Thanks, ladies and gentlemen.